Welcome back. In the previous few videos, you have been looking at how to graph piecewise functions. Today, we're going to just focus on adding in evaluating at a piecewise function. So we're going to go through the three graphs that you've already created, and we're going to just find the value of that function at a certain input. And then we'll look at a graph at the end that maybe you didn't do, or any piecewise function graph, and just talk about how we could evaluate. So first of all, when I ask you to find f of something, remember that just means tell me the output when the input is that number. So for instance, when I say find f of -4, I'm asking you to find the output when the input is -4. So I've got to really think about this. There's a couple of ways that I could find this output. One of them would be to look at the graph. So if I look at the graph, I'm going to locate where x is equal to -4. So here's x equal to -4. I've got to find a place on my function somewhere along this line, x equals -4. And it looks like I have a point right here. The value, or the output, is -3. So this is just equal to -3. Now, let's say we didn't have the graph, okay? Let's say we just had the function. So if we look up here, our function f of x, and I ask you to find f of -4, I have to look at which part of my function would x equals -4 fall on, right? So these are all of the values where x is less than 0. We would graph this function, and our output would be figured out by using this function. This would have all my inputs greater than or equal to 0, and then we could use x squared to calculate our output. So if I were just using the function, I have to first decide, where does my input fall? Is it going to be on this pink function or on this orange function? So let's look at f of 3. f of 3, okay. Is 3 going to be in an input value that's less than 0? So is 3 less than 0? That's what I'm asking myself. And I think we can all agree that 3 is not less than 0. Is 3 greater than or equal to 0? Yes, in fact it is. So I'm going to use the orange function here and plug in 3 into the function that's defining that part of f of x. And then I finish calculating. So f of 3 is 9. Okay, let's try another one. What about f of 0? So I have to ask myself, where does 0 fall? Is 0 less than 0? No, it's definitely not less than 0. Is 0 greater than or equal to 0? And I think we can all agree that yes, it is. So once again, I'm going to use the orange function to calculate, and I'm going to put in 0 as my input into this function x squared. And I'm going to get 0. Now we can verify both of these by looking at the graph. So f of 3, here's x equals 3. Along x equals 3, if I look at my output when x is 3, it's 9. For f of 0, there's where x is 0, and notice I have two possible places I can be looking, but only one of them has a closed circle. So we actually use this value right here, which is 0 as an output. All right, let's go ahead and try one of the other graphs that you did. Okay, so this was the second graph that you created in one of the previous videos. So let's go ahead and spend some time finding the value of the function at a variety of different inputs. So let's start with f of -2. So I want to know what's my output when my x, or my input, is -2. So I could either look at my graph and find where x is equal to -2 and see the value of my function there. And I have a value of a y coordinate of 0. So I know it's 0. Now I could also find that by using my function. And I ask myself, where does -2 fall in my choice of domains? Is -2 less than 1? Yes, it is. So -2 is less than 1 means that I will use x plus 2 to find out what my output is. So I would plug in -2 and I get negative 2 plus 2, which simplifies to 0. Okay, what about f of 0? So let's try using the equation first, and then we'll verify on the graph. Is 0 less than 1? Yes, it is. So I'm going to use that top equation, that top function, x plus 2. So I'd plug in 0 for x plus 2, and that's going to give me 2. Now I can verify that on my graph, right? So when x is 0, my output is right here at 2. Okay, let's try f of 1. So is 1 less than 1? No. Is 1 greater than or equal to 1? Yes. So we're going to use this function here to find out what the value of f of 1 is. So I'm going to use x minus 1. I'm going to simplify, or substitute 1 in for x, and then evaluate. So I would get 1 minus 1 is 0, and 0 squared is 0. So f of 1 is 0. I can verify this by looking at my graph. F of 1 means find when x is 1. That's right here. Now, once again, we have maybe 2 possibilities here, so you really have to be careful because only one of those is an actual closed circle. The closed circle, remember, means that you include that value on your graph. The open circle here means that everything up to but not including x equals 1 will be included on this part of the graph. Okay, let's move on to the third graph. So for your third graph, you had 4 different functions. So you really do have to be careful about checking to see which function, which part of that piecewise function will use the input that you want to find. So if we start here with f of negative 4, all right, now again, I could come over to my graph and I could say, okay, here's where x is negative 4. What's my output going to be when x is negative 4? Well, my output's going to be 1. So I know that f of negative 4 is just 1. However, I could also use the equations. So f of negative 4, so if I'm trying to figure out where does this fall in my required domains, let's look. Is negative 4 less than negative 3? In other words, is negative 4 to the left of negative 3? And it is. So we know we would use this function here. Now what's interesting about this is that it is a constant function, which means that no matter the input, the output will always be 1. So anything that had an input that was less than negative 3 will always have an output of negative or of positive 1. Okay, let's try f of 0. Now, once again, I could come over to my graph, locate where x is equal to 0, and I see I only have one possible output there, and that's 6. That's on my purple curve. I can also do this using the equation. f of 0, okay, so is 0 less than negative 3? No, it's not. Is 0 in between negative 3 and 2? And it is. So that's why we would use this function then to calculate f of 0. So let's go ahead and do it algebraically. So f of 0 using the function would be negative 0 plus 1 squared plus 7. So that's 0 plus 1 squared is going to be negative 1 squared plus 7. Now be careful with this. When you're doing order of operations, you square first, and then we'll take care of that negative. So 1 squared is 1, but we multiply it by negative 1 again, plus 7. So then we get f of 0 equals 6. And we got it both ways. Okay, finally, let's try a couple more here. F of 3. Okay, so is 3 less than negative 3? No. Is 3 between negative 3 and 2? Nope again. Is 3 in between 2 and 9? Yes. So this is the function I will use to calculate f of 3. Now that just happens to be my green function this time. So I'll plug in 3, and I have absolute value of 3 minus 6 minus 6. So f of 3 is the absolute value of negative 3 minus 6. The absolute value of negative 3 is 3 minus 6 and that ends up being -3. I can verify that on my graph by looking for when x is 3, what is my output? So if I look through my graph, when x is 3, there's my output at -3. And then finally, f of 6. So we ask ourselves, is 6 less than -3? Nope. Is 6 between -3 and 2? Nope. Is 6 between 2 and 9? Yeah, it sure is. So we're going to use that green function again. So I could either use the graph or I could use the function itself. I'm going to use the function again. So I'll have absolute value of 6 minus 6 minus 6. So that's a lot of 6's. That's an absolute value of 0 minus 6, which is 0 minus 6, which is just -6. I can verify that by looking at my graph. When x is 6, my function has an output of -6. Okay, now let's look at a kind of crazy graph here. All right, for our last graph today, we don't know the functions this time, the actual algebraic functions for this graph, okay? A couple of notes. First of all, even this picture doesn't have the arrows drawn at the ends of the graph. I'm going to go ahead and put those in because we do want this to go on forever. All right. First of all, let's go ahead and try and write the domain for this graph. Now, when I write the domain, I start looking from the left, okay? And I notice that my arrow is pointing down and to the left, which means -infinity is going to be part of my domain. Okay, we're going to go from -infinity and we keep going, we keep going, we keep going until we run into a hole in the function. Now, we look at the x coordinate of that hole and it's -3. So I say we can go from -infinity up to, but not including -3. Now, I'm going to pick up on the other side of -3. And I'm going to continue to travel along this function using all of those x values until I get to 0. However, I don't need to say we can't include 0 because look, up here we actually do have a value for 0. Okay, so we're still good. From -3, we don't have anything we need to worry about. We keep going, we keep going, we keep going until we hit this x value of 3. But once again, look, there's a point here when x is 3. So we can actually continue to move until we reach x equals 4. Okay, so we have all the x values from -3 to 4. And then we have an asymptote. So we'll go around the asymptote, and then we see it continues to travel all those x values, and then we have the arrow, which means it will continue to go to infinity. So our domain is -3, or -infinity to -3, -3 to 4, and 4 to infinity. Now, range can be found a number of different ways. If you want, you can actually rotate your paper and kind of think of range in the same terms that you would think of domain. I'm going to sort of go from the bottom of my paper up, and this can be a little strange because with range, you can have multiple outputs that are the same. All right, for instance, this is going towards infinity and so is this. Okay, so we have these two that are including all of those y values that are not seen on the graph below what we have. So from -infinity on the y-axis, that was a terrible infinity, we look as we move up. Okay, so we're moving up in the function, and I'm looking for holes on this function anywhere. Now, I see there's a couple of holes on the function here, okay? So this has a y value of 0. So before we jump and say we can't use a y value of 0, is there any other place on the graph that does have a y value of 0? And I see plenty. I see at least 3 other places. So I don't need to take 0 out of my range. Now, as I continue to move upward, I notice there's another hole at y equals 1. But again, I ask myself, is there someplace else that has an output of 1? And there is over here. So I don't have to take y equals 1 out of my range. As I continue to move up, I see another hole here at y equals 2. Once again, I ask myself, is there someplace else that has a y value of 2? And there is. So this hole doesn't really affect anything in my range. As far as this goes, this doesn't really affect my range at all because anywhere I go, so y equals 4, I have a y value there, okay? If not here, there will be one way out here somewhere, okay? But then I notice that we continue to go up and to the right here. We continue to point up, which means my range is going to continue to move out towards positive infinity. So there really aren't any values in the range that can't be included. Okay, let's go ahead and go through these evaluations together now. So I want to evaluate f of -4. Now we don't have a function to use, an actual equation, so I'm just going to use my graph. I find out where is x equal to -4, right here, and what is the value of the output there. So that's the point -4, 0. So my output would be 0, just using the graph. How about f of -3? Once again, looking at -3. Now this is interesting because this is the only place that I can see on my graph that has an input of -3, but it's an open circle, which means we don't actually have an output when our input is -3. So this is one that we would say is undefined. Okay, how about f of 0? Now, you might initially jump and say, oh, it's another open circle, so it's undefined. But don't forget to look at all places where x could be 0, because x equals 0 actually does have an output at y equals 3. So our output is 3. Okay, how about f of 2.5? So that's this line right here. I don't see anything here, but I do see something here. So when x is 2.5, when my input is 2.5, it looks like my output is going to be 2. Okay, how about f of 3? All right, so I look up here and I see an open circle and I say, okay, it's undefined. However, don't forget to look everywhere where x is equal to 3, because we actually do have a point when x is equal to 3, and the output for that point is -1. And then finally, f of 4. Now, anywhere I go when x is 4, I'm not going to get an input. Or I'm sorry, I'm not going to get an output because there's an asymptote there. It's a vertical asymptote, which we learned in our previous unit that a vertical asymptote cannot ever be crossed, which means we will never have an input of 4. So that's another one that will be undefined. All right, nice work. Go ahead and check Classroom for your assignment.